Hello. Okay, so let's summarize what happened in the previous lecture. So we studied the multi-path channel, and so here is the wireless channel. Okay, and the input is a complex baseband signal, some baseband signal S of t, and then it goes through the wireless channel, which typically includes the loss stages of the transmitter, the medium between the two antennas, the front end of the receiver, and so on. So basically the wireless channel is the physical channel and also parts of the transmitter and receiver. So there are snakes in there, up converters, down converters, so these are oscillators. There are amplifiers, there are digital to analog converters, analog to digital converters, and so forth. Okay, and so there are many things going on here, but we can just abstract it as part of the channel. And what you get is basically this. So this is your input signal, which is S of t. Now what you get is basically the signal delayed and then multiplied by this phase factor, and then you have an amplitude factor, complex amplitude factor, and then you have a sum because you receive the signal through a number of paths. And the delay is a very complicated function if there is mobility, but using some assumptions, we can actually simplify our received signal model into basically a sum involving the transmitted signal with fixed shifts, with fixed shifts or delays with a delay tau n specific to the path n, and then there will be this phase factor which is a complex sinusoidal signal with frequency f Doppler. And the Doppler frequency is V over lambda. Lambda is the wavelength at the carrier frequency, so it is C over the carrier frequency, and then multiplied by cosine theta n. What is cosine theta n? So basically, if this is the path to the receiver, this is the nth path, and this is the direction of motion. Here I'm assuming that the transmitter is fixed and the receiver is moving, but the same is applicable if both are moving actually. So this is the direction of motion of the receiver. Then basically theta n is this angle between the path and the direction of motion. If the two terminals are moving, basically I think in homework 3 I will give you like a general formula for the Doppler shift. So this formula is like, again, is for like stationary transmitter and the moving receiver, but you can generalize it as you will see later. Okay, so this is basically our formula, and still it is not that manageable. Okay, and it can be written as a sum, or sometimes for convenience we will assume that the both delays tau n are rather than being discrete, they are continuous, and we can represent the model as an integral. Okay. Now, if there is no motion, no mobility, the speed is equal to 0, and so if the speed is equal to 0, you can see it in the Doppler frequency is 0, and basically the time dependence through this term here will disappear, and so this guy will become a 1, and your channel is like an LTI filter with impulse response alpha of tau. And this filter has a frequency response, which is the CT-FT of the impulse response. And so at the end of the previous lecture, I said that our next task will be the correlation function of h of f1 and h of f2. So basically, we model the channel as basically a random process, and we are interested in the correlation function here, in the frequency correlation function between the response of the channel at frequency f1 and the response at frequency f2. Okay, so these are generally two different frequencies, and we want to study the correlation. How is the channel gain at f1 and how are the channel gains at f1 and f2 correlated? And so what we do is we write down a formula for h of f1, a formula for h of f2, and so each one of them is an integral. So basically their product will be this double integral, and then we take the expectation. Expectation, because so when you take expectation, it means that there are random variables living in there. And so what are the random variables? Basically we assume that the complex gain of the channel is a random variable. So we will take the expectation here, and it's applicable to those alphas. So because we have expectation, h of f1, h conjugate of f2, it's an expectation of a double integral. Okay, and so it's not always valid to interchange the order, but if you assume that basically B of tau, remember last time we talked about B of tau, it's the multipath intensity profile, and it is the expectation of magnitude of alpha tau squared. So if this function is integrable, then you can use Fubini to argue that it is valid to interchange the order of expectation and integration. So you can take this expectation inside, and it will be applicable to the random variables in there. So those are alpha t tau and alpha tau prime. Now, if you don't do further assumptions, you are stuck in this expression. So basically, that like the most widely used assumption now is to assume that for a tau different than tau prime, which means that we are talking about two different paths, okay, two different delays, the channel gains, the corresponding channel gains are uncorrelated. Okay, so the assumption is the expectation of alpha tau, alpha conjugate of tau prime, that this will be delta. So there will be a Dirac delta of tau minus tau prime, which, as you know from random processes, this Dirac delta is used in the correlation function of a white process to indicate uncorrelatedness. So we will use it to indicate that, if tau and tau prime are different, then basically we don't have correlation. Okay, so this will make life much easier. And if tau is equal to tau prime, so we have the power here, so this will be expectation of magnitude alpha tau squared. Okay, so it's again what you know from stochastic processes as a white process. So this assumption in the context of wireless communications is called the wide sense stationary uncorrelated scattering assumptions, WSSUS. Okay, and this is what we'll use here in this course. Okay, it means that this expectation is P of tau multiplied by a Dirac delta tau minus tau prime. And of course, once you see the Dirac delta, you know that your double integral will collapse into a single integral. So life will be easier now under this assumption of uncorrelated scattering. Okay, so basically you can do the integration with respect to tau prime and replace tau prime by tau, and you get just a single integral now. Much more manageable. Okay, so this is again one of the fundamental assumptions that are used a lot in wireless communications, and it will lead to this expectation being equal to the integral of P of tau e to the minus I 2 pi, the difference between the two frequencies. So this is something nice happened when we did the integration with respect to tau prime. This tau prime was replaced by tau, and now you can take tau as a common factor and you get a difference in frequencies. Under the WSSUS, you start by studying the correlation function between the channel frequency response at F1 and at F2. Generally speaking, this is a function of F1 and F2. It's a function of two variables. But under our uncorrelated scattering assumption, what you get is a function that depends only on the difference between these two frequencies and not on their exact values. Okay, so you take this assumption, you apply it. Basically, what you get is something that depends on f1 minus f2. And so if you increase f1 and f2 by a fixed quantity so that their difference is the same, the correlation function is the same. So now our correlation function under our assumption becomes a function of a single variable, not two variables. I can just say that it is a function of delta f. Okay, so now this is a function of delta f, and so it's called the spaced frequency correlation function. Correlation function. Again, this is not general. You know, if you don't invoke this assumption, you will end up with a formula that generally depends on f1 and f2. But under our assumption, you can basically write down things in terms of the difference. And another good thing happened here, which is basically if you write the difference as delta f, so you have the integral p of tau, which is the multipath intensity profile, e to the minus I2 pi delta f tau. Well, and you integrate with respect to tau. That's exactly how we define the continuous time Fourier transform. Okay, so in this case, we will have the spaced time correlation function, which is this guy here, but under our assumption, we get a function that depends only on the difference between the two frequencies, and this function is exactly equal to the CTFT of B of tau. So the spaced frequency correlation function, it's as if you take the, under the assumption of uncorrelated scattering, it's as if you take the Fourier transform of the multipath intensity profile. Remember that this thing here is, as a function of tau, it's the expectation of alpha of tau squared. And typically it is a decreasing function with a certain width going from some tau min to some tau max, okay? So this is basically the spaced frequency correlation function, and from it we will now talk about the concept of the coherence bandwidth of the channel. Any questions?
Doctor?
Yes.
The wide since stationary, it is the same as the weak stationary?
Yes. Some wide sense is stationary. Sometimes it's called weakly stationary. So, yeah.
Yeah. Okay.
So now the spaced frequency correlation function and the multipath intensity profile. So they are now guys related by the CTFT, okay, in one way, and the inverse CTFT in the other way. And hence, from the uncertainty principle in Fourier analysis, the width of this function is related to the width of this function. So the uncertainty principle, it tells you that for well-behaving functions, what you have is that the width in the time domain is, you can say it's a factor over the width in the frequency domain. Okay, so basically something like this. Okay, in the study of the uncertainty principle, there is a specific definition for the width of a function, but it's not needed here. You can just take, again, as I said in the previous lecture, width is like an ambiguous concept, and here we do not need actually to be precise. But the intuition is sort of independent of how you define the width of a function. You can make several arguments why, if you have something that gets wider in the time domain, it gets narrower in the frequency domain, and vice versa. Okay? So, since these two guys are related via a Fourier transform, they are a Fourier transform pair, then this means that the width of this guy is the reciprocal. or it's proportional to the reciprocal of the width of this guy. So the width of the spaced frequency correlation function will be given this name, the coherence bandwidth of the channel. And the width of the multipath intensity profile is the delay spread. Okay, so you have here the minimum delay and the maximum delay. Okay, and this is P of tau. It has a width, again, because you start receiving your signal and then copies of that signal, and typically as the delay increases, you get the signal more attenuated, and then after some delay, basically the received paths are sort of indistinguishable from the receiver noise, and so you can just ignore them. So the width of the multipath intensity profile function is the so-called delay spread, the multipath delay spread. And now the width of this function is the coherence bandwidth of the channel, and I will talk about its meaning in a minute. Then they are the reciprocal of one another. So we have this relationship here, which is very important. Because when you read a paper or a reference about wireless communications, you may hear people describing things in terms of the coherence bandwidth of the channel, or they may talk about the delay spread. And if they talk about if they use one term, you understand basically this relationship, that basically the coherence bandwidth is the reciprocal of the delay spread and vice versa. Okay, what is the meaning of the coherence bandwidth of the channel, which is what is the meaning of the width of this correlation function? Remember that this function is expectation h of f1, h of f2 conjugated like this. Okay, so let's try to understand this. Suppose that the width of this function is 1 megahertz. Okay, and suppose that delta f, so you are talking about two frequencies f1 and f2, the difference between them is 1 kilohertz, and definitely 1 kilohertz is much smaller than 1 megahertz. Okay, then if delta f is much smaller than pf, okay, if we are talking about, so basically this is the spaced correlation function. Let's draw its magnitude. It looks something like this. Okay, perhaps something like this, and this is delta f. Okay, it has a certain width. So if delta f is a small, okay, if delta f is a small, then basically the correlation is high, which means that the spectral components of the transmitted signal at frequencies f1 and f2 encounter highly correlated channels. We can say that the spectral components of a transmitted signal, so the transmitted signal has a bandwidth. It has frequencies from -w to w. So take two frequencies, f1 and f2, separated by this number here, 1 kilohertz, which is much smaller than the coherence bandwidth of the channel. It means that those two spectral components of the signal, they encounter almost the same channel. Okay, so this happens if delta f, if the separation is much smaller than the coherence. So the coherence bandwidth again is sort of the width of this thing. Now, if delta f, if the separation is large, so we are talking about a large delta f here, then the spectral components encounter almost uncorrelated channels. Channels that are uncorrelated, or you can basically push things further and say that they are independent. Since the correlation is high for a small separation, okay, so when you study correlation, right? When you study correlation, okay, so this is something. It's not different from what you studied earlier about. I mean, not in this course, in 241 about the correlation function of a random process, right? So, basically, this thing here in magnitude. So the magnitude of the correlation is always upper bounded by, right, by the Cauchy-Schwarz inequality. So this is upper bounded by this thing here, the expectation h of f2 squared, right? And hence, basically, So okay, let me write it in terms of like conventional random processes. So if you have a random process, let's say x of alpha. Okay, so the correlation function cxx of tau is expectation x of alpha, x conjugate of alpha minus tau. So this is, I mean, for a stationary process, this is upper bounded by, again, by the Cauchy-Schwarz inequality, the expectation of x of alpha squared, expectation of x of alpha minus tau squared. So tau is the shift, right? And if the process is stationary, then these two expectations are the same. So what is this thing here? It is cx of 0, right? So basically the correlation, so the typical thing is, okay, so let's put it this way, in a more objective way. So the correlation function of any wide sense stationary process is upper bounded by its value at a separation of 0. Okay, when you have that the separation is equal to 0. Okay, so again, this is clear from the Cauchy-Schwarz inequality by definition. So by defining the correlation to be like this, then cxx of tau is always less than or equal to cxx of 0. Okay, so basically the correlation function can do other things. So it becomes high at 0, and then it drops. Right? It drops. It may go back. I mean, so there are periodic correlation functions. Okay, so the correlation function may go back to 1 at some separation. So let's say here for tau star, it may go back to 1. So there is a class of correlation functions that basically you have high correlation. So the highest correlation is at 0. This is granted for every wide sense stationary process, but it may be high also in a periodic fashion. Okay, and there are conditions to have this. The other thing is basically you have high correlation at 0, and then you decay. You never go back to this high value. Okay, in both cases, if you are around 0, if tau is very small, then this is the highest correlation. Okay, so for a wide sense stationary process, a small separation, okay, is sufficiently small separation means that the correlation is high. Now, if the correlation gets large, is it true that the correlation may not get higher again? Generally speaking, no, because actually the correlation function may be periodic and may reach this highest value again and again and again. But the functions I'm talking about here in wireless communications are typically of those type, in which they have the highest value at the oil, and then they start decaying. But of course, there is one correlation function, so they start decaying, but then you may have riddles, so you start getting high and low, and we will see actually another example in this lecture like this. But the typical thing is that there is sort of a so-called the main lobe, okay, and then there are side lobes, and you never go back to the high value. Okay, so that's a good question. So yes, there is an implicit assumption in my correlation function, or the correlation function is here. I mean, there is this one, and then there will be another one that they are basically they have like sort of a main lobe. And then if they have a non-monotonic behavior, then it's basically far from the origin, and with the small values. So again, if delta f is small, the correlation is high. If delta f is large, the correlation is low. Now, small or large relative to what? Relative to the width of the correlation function, which is called the coherence bandwidth of the channel. Okay, so suppose that your signal has a bandwidth W. So basically every frequency in the signal is between minus W and W, and W itself is less than or equal to the coherence bandwidth of the channel, which is the width of the correlation function. What does this mean? It means that if you take any two spectral components in the signal, they are separated, they are within W from one another, right? and so they will be separated by much less than the coherence bandwidth of the channel. So a signal with a W that is much less than BC, all the signal, all spectral components of the signal will encounter almost the same channel gain. Okay, so basically the channel here, we don't really need to focus about like, you know, H as a function of F. We can here represent the channel as just one complex number, as we will see. Okay, so this is actually the main model used in this course and the main model that you will encounter in many papers. It's, you know, it has several names. Flat fading model, flat fading, which is this flat, I mean, a flat function means a constant function. Okay, so what we are saying is that if the bandwidth of the signal is much smaller than the coherence bandwidth of the channel, it means that if you take any F1 and F2 in the signal, delta F will be much smaller than the coherence bandwidth. So basically, all spectral components are almost seeing the same channel. Okay, and so it's like they encounter just, you know, not a function H of F, but just a single constant number. Okay, so it's called flat fading model, or frequency non-selective fading. So non-selective, which means that each frequency in the signal sees the same thing. Okay, so there is no, you know, there is no like frequency encountering some channel gain and another frequency component encounter another channel gain. And also called narrowband. So remember, narrowband, it's, as I said in the previous lecture, it's one of the overloaded terms in communications. It's used to indicate many things. Now I am using, so in the previous lecture, narrowband, I used it to mean that the carrier frequency is much larger than the bandwidth of the signal. So here I am using it to mean that the coherence bandwidth of the channel is much larger than the bandwidth of the signal. Okay. So now you can explain this story using the delay spread rather than the coherence bandwidth, because the coherence bandwidth is the width of the spaced frequency correlation function, and it is the CTFT of the multipath intensity profile, and so basically the delay spread is almost the reciprocal of the coherence bandwidth. Okay, so here is the story, like sort of in the time domain. The symbol duration is again approximately the reciprocal of the bandwidth of the transmitted signal. Flat fading means that W is much smaller than the coherence bandwidth of the channel. So the bandwidth of the signal is much less than the coherence bandwidth of the channel. So 1 over W is much larger than the reciprocal of the coherence bandwidth of the channel. So what is this guy? This guy is almost the delay spread of the channel. And what is 1 over W? It's almost the symbol duration. Okay, so flat fading or narrow band or frequency non-selective fading, you can also describe it as the operation under basically this inequality in which the symbol duration is much larger than the delay spread. So you can describe it in two ways. You can say that the bandwidth of the signal is much smaller than the coherence bandwidth of the channel, or you can say that the symbol duration is much larger than the delay spread of the channel. Okay, and to have like sort of an intuitive feeling of what this thing, or have like some visualization of what's going on, let's basically show this case. Okay. And I will assume, you know, that you transmit, you know, the baseband, the signal is just those rectangular pulses, bipolar pulses, and I will assume, you know, that everything is real valued. In practice, basically the symbols are complex valued quantum constellations, and the channel itself must be modeled as a complex number, because it makes a change to the magnitude and phase of the signal. But ignore everything, assume that everything is real valued, and, you know, ignore noise. I mean, in the receiver also there is noise that is added to the received signal. Ignore this. Okay, so this is the transmitted signal. So basically a sequence of pulses. So this is the first pulse, and then second one is negative, then positive, negative, positive, negative. Okay, and so this is the transmitted signal. Okay, And so what will happen? You basically transmit this signal. You do not transmit this signal as drawn here. Basically, it is up converted, it is amplified, it is transmitted via the antenna, and then in the receiver it is received, it is amplified, and then it is down converted. So what you get is a delayed copy. A delayed copy. So suppose that this is the first copy of the received signal at the receiver. It will come with some amplitude, alpha of tau min, okay, and this is the same. So basically those are basically 1 and 2 and 3 and 4. Now they are received. How they are related to the transmitted signal, they come with a certain amplitude, and they are delayed in time by tau min, okay, which is the time needed to go from the transmitter to receiver, because the propagation speed it's a huge number, you know, for electromagnetic waves, but still it is finite, and so there will always be some delay between the received signal and the transmitted signal. Okay, but our basically channel is a multi-path channel, so you do not just, so basically this is the transmitter and this is the receiver. We do not just get, for example, this thing, if there is a line of sight, there is also a scatterer here, and this part of the transmitted signal will go and hit the scatterer and then go to the receiver. So this will come with further delay, okay? So this is another copy of the transmitted signal at the receiver. It comes with a certain amplitude and with a certain delay here that is a bit greater than tau min. Okay, and you may get in a rich scattering environment, the environment is full of scatterers, and so you get so many of those copies, and then basically you may get, after, you know, this is the copy or the replica of the transmitted signal that you get at the receiver after the maximum delay tau max. We are assuming that after that, if there are received copies, they have negligible magnitude, so they are indistinguishable from the noise. Okay. So again, what you get at the receiver is copies. Okay, replicas of the transmitted signal. Each copy comes with some parameters. So basically, it has amplitude and delay, and of course, things in reality are difficult. You need to include complex phase term and so on, but I mean, for now, this is just to visualize what is going on. So what I did in drawing this plot, I assumed that the separation, so the difference between tau min and tau max is very small relative to the symbol duration. Okay, so this is this inequality, that the symbol duration is much larger than the delay spread of the channel, which in the frequency domain we will say that the bandwidth of the transmitted signal is much smaller than the coherence bandwidth of the channel. So what will happen is the following. Okay, so in the receiver you will take samples. So suppose you take a sample at this instant of time. Okay, at this instant of time you take a sample. Okay, now when you take a sample, okay, of course, what you get in the receiver, those guys will come added together. Okay, so those guys come, you get their sum in the receiver. I say, we basically assume that basically those replicas or copies, they are summed. Okay, so again, it's a fundamental assumption that we assume that the wireless channel is like a linear system. Okay, and so you get a sum of those signals. Something very nice basically happens here. If you sum basically if you sample the sum of those signals at this time instant, your sum will depend on just one transmitted symbol, which in my case here is the second symbol. Okay, so basically those waveforms are offset with respect to one another, but the shifts are small relative to the width of the pulse, and because of that, again, if you take a sample, okay, it will depend on, for example, at this instant of time, on the second symbol. At this instant of time, okay, so that's the seventh symbol and nothing else. So basically, what you get if you take a sample, then it depends on one symbol, and then this symbol will be so you take a symbol, you will get a symbol, and it will be multiplied by alpha tau min plus alpha tau 1 plus till alpha tau max. Okay, So basically those guys will be added, and your symbol sort of can be taken as a common factor. So this is where you have flag fading or frequency non-selective fading, and it happens again because the symbol duration is much larger than the delay spread, and so you get many replicas, but they come with delays that differ from one another in a way such that if you take a sample, it will basically depend on just one symbol. Contrast this with the case in which the delay spread is significant. So if the delay spread is significant, so here, this is the first copy that you get in the receiver, this is the second copy. Now you see that the delays are significantly, they are significantly different from one another, and the delay spread will be different from t. So here is tau min, tau min. So those are the replicas. Again, you get a sum of these, okay? But now the delay spread, which is tau max minus tau min, is much larger than big T, which is the symbol duration. Let's see what happens when you take a sample. Now, when you take a sample, let's take it here. Now, your sample does not depend on just one symbol. It depends on symbol 6. It depends on symbol 4. It depends on symbol 3. We have ISI, inter-symbol interference. Right? We have ISI, which means that again, you take a sample, you sample your received waveform, and at an instant of time, your sample does not depend just on one of the transmutables. Here, it depends actually on 3 symbols. Okay? So making detection very, very difficult. Okay, because now when you detect, basically your received signal, it's not just noise plus some symbol, it's noise, and now we have 3 symbols, and each symbol is of course multiplied by the respective alpha of tau. So here, if you have a system that is like this, so this system can be called wideband. So this is a wideband system, okay, and by wideband you mean basically that the bandwidth of the signal is much larger than the coherence bandwidth of the channel. Or in the time domain, basically the reciprocal of this guy, which is the symbol duration, is much smaller than the reciprocal of this guy, which is the delay spread. In this case, you have inter-symbol interference. If you want to write an accurate model for your received signal, I mean accurate from a practical point of view, I mean we have already done many assumptions, but to make something that actually works, you will have to take this into account. You will have to have your received model as a sum over a number of symbols, and the number of symbols in your sum will basically increase with increases in the delay spread relative to the symbol duration. Okay, so here the channel is actually modeled as a multi-tab filter. It's like a filter, and you are convolving the sequence of transmitted signals with a non-trivial filter. But flag fading is like a trivial filter. Basically, it's just at an instant of time, your signal is just the one of the transmitted symbols multiplied by something. That's it. And you need to focus on that symbol and try to detect it. But here we have inter-symbol interference, and life becomes very difficult. Okay? So initially in this course, our focus will be flag fading. Okay, our focus will be this model, and hence, when we study received signals, you will not find the summation or anything initially. Okay, and then we will basically see how basically modern systems deal with this scenario. I mean, modern communication systems cannot operate directly in this scenario. Why? Why this thing here is like is not good to use in practice, right? So here T is much larger than the delay spread. It means that the symbol duration is large. What does this mean in terms of the rate of transmission? Low rate, perfect. Low rate of transmission. If the symbol takes so long to transmit, then the number of symbols that you can transmit during unit time, during 1 second, will be small. well, I mean, so you will have to have no rate transmission, and this is not what we want. We want high rate transmission. We want to transmit as many bits per unit time as possible. So how can we have this model and have a signal actually that is high rate? Okay, so that's the O of the M trick that we will learn later in the course. But for now, we will focus again on this one. Once you understand this one, you will be able to upgrade to O of the M. Okay, so these two figures are basically very important to I know the stuff here is ambiguous: delay, spread, coherence, bandwidth, and so on. But keep this picture in mind, and single duration, delay spread, single duration much larger than the delay spread, then the multipath effect is there. It is there, but the nice thing, if take one sample in the receiver and it depends on just one symbol, if the delay spread is large, then actually you are in trouble and you get basically something sophisticated like this, and the received signal at an instant of time will depend on several or perhaps many of the transmitted signals. Okay, any questions? Okay, so now remember I talked about the channel as if it's LTI, so basically we ignored this factor e to the I2 by f Doppler t, and so now we want it back. Okay, so we want it back, but from now I will assume that the flat fading scenario. So flat fading, which means that the delay spread is much smaller than the symbol duration, or the bandwidth is much smaller than the coherence bandwidth of the channel. Okay, and now, as we have seen on the previous page, basically the received signal, what you can do to it is that you can basically assume that what you have is one symbol, okay, that is multiplied by summation. Okay, so again, this is the picture. So if you have pulses, they are shifted slightly from one another, okay, so that when you take a sample, it's basically the same symbol. It's the same symbol, and then you have the sum of the alphas. Okay, and so now what we can do, assuming that the delay spread is much smaller than the symbol duration, and so the delay is approximately tau, because the delay spread is small, it means that the difference between tau min and tau max is small. You can just say that there is some delay tau zero. Again, this is to model, to get something tractable. Then our received signal model, you do not need the convolution integral. Okay, so this is flat fading. Flat fading, you don't need convolution to model the received signal. What you need is basically a symbol multiplied by the integral or the sum of basically the alphas, and now I am restoring basically this dependence on time, because this is the game actually, right? It's a model communication system in which like the terminals are moving, scatterers are moving, and so forth. Okay, so now our model will be a symbol, okay, S of t minus tau, and it's multiplied by g of t, and g of t is basically the sum or integral of alphas, and now we have also those guys, e to the I2 by fd of tau t d tau. Okay, so this is the time varying channel gain. This is the time varying channel gain. Because it is a summation or an integral, it carries, it accounts for multipath effect. Now, what again? Question about correlation. How is the channel gain correlated across time? So what is the correlation between G of T1 and G of T2? So we want to study. So now suppose that the channel now has some gain after 100 milliseconds. How is the gain after 100 milliseconds related to the gain right now? Okay, because now everything is changing with time. Okay, we have G of T, and so how is basically the channel gain correlate across basically time? So we will basically take g of t. We write g of t1, g conjugate of t2, and so basically each one of them is an integral, and so we have now a double integral with two dummy integration variables, tau and tau prime. And don't forget that this is with a conjugate, so one of these guys will appear with a minus sign, and then apply expectation, and then using the previous assumptions, so we can assume that the multipath intensity profile function is integrable, and so we can apply Fubini to justify basically taking the expectation inside. You can also use the white sense stationary uncorrelated scattering assumption, so that you can write down basically the expectation of this product as B of tau multiplied by Dirac delta. The Dirac delta is so nice here because it will reduce your double integral into a single integral. But of course we need more than what we did previously, because now we have additional random variables. When we set v equal to 0, we only have alpha. But if v is generally not equal to 0, now we have the other random variables, which are the thetas, the angles. Remember, so basically this is the receiver, this is the path. Okay, so this is nth path. Okay, or now we are doing parameterization with tau, so this is path with delay tau. Okay, and there is a direction of motion. Okay, so this is direction of motion. Okay, and there is an angle between them, which is theta. And each path, so basically if you have two paths, you have different angles. Okay, so the direction of motion is the same, but the path come to the receiver from different directions, generally speaking, and so these are two different angles. And so now, if you go to this integral here, we have actually four random variables: alpha tau, alpha of tau prime, theta of tau prime. Now, first order of business to make life easy is to assume that the alphas are independent of the thetas. The alphas are independent of the thetas. Okay, so those angles are, if you treat them as random variables, they are random variables that are not related to basically the amplitude gains. Okay, and so when you apply Fubini and take the expectation inside, you can actually take the expectation of these two guys alone. Okay, right? If you have uncorrelated functions, expectation of a product, right, is product of expectations. So basically, this is what we're doing. So you apply the expectation. If the guys are not correlated, then you need to take the expectation basically for every random variable at once, using the joint distribution or whatever horrible thing you have. But assuming uncorrelatedness, basically you have this expectation, and then you have an expectation which involves theta of tau and theta of tau prime. Okay, so you can basically do the expectation separately because of this assumption. So we assume this thing here, that basically alpha and theta, even for the same path, they are uncorrelated. Then you will go to basically this expectation here and apply white sense stationary uncorrelated scattering. So this thing here, you will write it as P of tau delta tau minus tau prime, and then you will do the integration with respect to tau prime. Okay, and so what you get is this. We still have one more expectation to handle because again, so this statement here, which I did previously, is a statement regarding basically the correlation function of alpha, but we need to talk about theta. What is theta? What is the distribution of angle theta, and so on. And so we still need to have this expectation here. So it's an expectation with respect to theta. Okay. How can we evaluate an expectation? Well, I mean, if you want like some closed form or something, then you need to provide a distribution. So what is the distribution of theta of tau? So theta of tau again is basically the angle between basically path with delay tau and the direction of motion. So what is a good model? So in a rich scattering environment, so very rich, so basically every terminal is surrounded by scatterers from all directions, in such environment, it is reasonable to assume that you will basically get your received signal from all directions. So basically, it's likely to get your, so that each path can reach you from any direction. Okay, so but this again, this relies on the fact of the abundance of scatterers in the environment. Okay, under this assumption, the rich scattering environment, which is like valid in a dense urban environment, for example, you can assume that theta is uniform from 0 to 2 pi. Okay, so this is basically our assumption. We'll assume that theta is uniform from 0 to 2 pi, and so our expectation now can be evaluated. Because I mean, you can apply lotus, right? So expectation of a function of a random variable, right? Expectation of a function psi of theta is basically you take psi of theta multiplied by the PDF of theta, and then you integrate. Okay, so this is exactly what we'll do here. Uniform from 0 to 2 pi, and so the PDF is 1 over 2 pi, and then you have an integral from 0 to 2 pi, and this is basically what we are integrating. Okay, and of course I'm assuming that every theta of tau, regardless of tau, is uniform from 0 to 2 pi. So basically this is a universal distribution to applied to any path. Okay, so now if you do this assumption, you will get an integral that does not seem to be doable, right? So your integration now, so we started with this expectation. We said, okay, let's basically assume the most simple thing, which is that theta is uniform from 0 to 2 pi, and so you get something like this. Okay, e to the I 2 pi v over lambda, and then the difference again when you apply uncorrelated scattering, basically rather than having T1 alone and T2 alone, they will be combined as a difference, something like happened before to F1 and F2, and so you will get delta T, let's call them delta T, and then cosine ADA. So what is this integral? Well, this integral actually it does not have a closed form, but it has a name because this integral is, it appears in lots of applications, and this is a Bessel function. Okay, so this is the Bessel function of first kind. Okay, and this is of order 0. Okay, and so this is something you may look. It's a very useful function, and it appears in several places in communications, propagation, physics, many places. Okay, so this integral again, the best that we can do for it is basically to represent it in using the standard Bessel function, and this one is basically J of 0, and now this is our correlation. Okay. So our correlation function, again, under our assumptions, okay, so many assumptions, okay, it becomes a function only of delta T. So so we started by saying, okay, how is the channel at T1 and T2 correlated? Generally, this will be a function of T1 and T2, but now we see that it does not really depend except on the difference, okay, delta T is T1 minus T2. And this Bessel function, if you plot it, so what is this correlation function? The Bessel function, it looks like a sink, okay? It looks like a sink, something like this. And so this is like related to the question I received earlier in the lecture, that correlation functions typically in wireless communication, again, a correlation function for a wide sense stationary process, its peak is at a lag or separation of 0. And then what happens next? So basically we are talking here about the family of correlation functions that start high and then decay. They may decay fast, they may decay slow, but they decay. And so they have typically a named loop, and maybe we have some oscillatory behavior for basically large arguments of the correlation function, but with a small correlation. Okay, so it never, basically never go back to high correlation again. So this is the sort of the typical time correlation function, and this model here, I mean, in some papers it's called or referred to as the Jakes model. Okay, Jakes model, and this time correlation function with the Bessel function is widely used. You will see it a lot. Okay. Now the time correlation function, the time space correlation function, it has a width. Okay, it has some width. Okay, you can take the width to be this thing or to be this thing. Again, width is ambiguous, and this width is called the coherence time of the channel. The coherence time of a very important concept in wireless communication. So, and you don't really need to be precise about it. Okay, you need basically the following argument. So a channel, it has a certain correlation function, depends on, you know, basically many things. This correlation function will have a width, which is the coherence time of the channel. Now, if you study two time instants that are separated by much less than the coherence time of the channel, so suppose that the coherence time of the channel is 1 millisecond. But then you study the channel now, and you study it after 1 microsecond. So the time separation is much smaller than the coherence time of the channel. Then the channel at these two time instants that are separated by much smaller than the coherence time of the channel gains will be highly correlated. In fact, we will idealize things and take them to be constant. Okay? So basically a delta t that is much smaller than tc, basically the channel gains at the two time instants are highly correlated. So suppose that you measure the channel gain now. If you wait for a time that is again much smaller than the coherence time of the channel and measure the gain again, if the gain initially was high, most likely it will be high again. If it was low, it will be low again. It's highly correlated. But if you study the channel, you know, after a time, you know, basically a time larger than the coherence time of the channel, most likely the new gain of the channel will be uncorrelated with the old gain. So you may measure, like, suppose that again the coherence time is 1 millisecond. Okay, so 1 millisecond coherence time, Tc is 1 millisecond. So suppose that this is T1, okay, T1, and this is 1 millisecond. Suppose that you study the channel again T2. So basically the separation between T1 and T2 is larger than the coherence time of the channel. And so here, GT2 and G of T1, so the channel gain here and there are uncorrelated. And in fact, again, to make life easier, actually we'll assume later that they will be independent. Okay, which is a much stronger statement, but actually we need it like to, when we do like performance analysis, compute probabilities of error and so on and so forth, we will actually go for independence. Okay, now this is the correlation. This is the correlation function under many assumptions. Okay, so if you plot it, and focus on the width of the main lobe, you will find that it's approximately 1 over v over lambda, and so this is typically taken to be the coherence time of the channel. So the coherence time of a channel is approximately 1 over v over lambda, or Tc is lambda over v. Don't take this expression seriously. Okay, it's sort of proportional to, but actually this is what is needed, even like if you want to design a practical system. So this very sort of simple expression, it tells you what? It tells you that as v gets larger, so if v increases, what happens to the coherence time of the channel? It goes down. Makes sense. This is very reasonable, right? Because if mobility increases, if the terminals are moving with higher and higher speeds, it means that things are more dynamic. And so you expect things to change faster. Okay, and so this will be basically represented with a small coherence time. Small coherence time means that basically to get high correlation, you need, you know, very small separations in time. If v tends to 0, which means that there is no mobility, no time variations, then the coherence time is sort of very, very, very large, which means that the channel is almost stationary, is almost constant in value. Okay. What about the dependence on lambda? You find here that the coherence time depends, it's proportional to lambda. So if the wavelength decreases the coherence time becomes less. Okay, and we will talk about this. I mean, you know, when the coherence time gets less, I mean, this becomes problematic in terms of channel estimation. And so like in a couple of lectures, I will give more details about this. Okay, but for here, I will just highlight something. Like people now are talking about millimeter wave communications. So millimeter wave communications, relative like to communications that that happens at standard radio frequencies, 1 gigahertz, 5 gigahertz. If you use millimeter waves, lambda is smaller, and so this means what? The coherence time is small. Okay, so again, this gives you like a rule of thumb. Do not take this expression seriously, but the dependence between TC and lambda, the trend is very good. And you will basically talk, hear people talking about, oh, we are using a higher carrier frequency, and so the coherence time is small. What do they mean by this? If the carrier frequency is high, then lambda is C over F carrier. A high carrier frequency, so the carrier frequency is say 60 gigahertz rather than 6 gigahertz. If this number is high, then lambda is small, and it means that the coherence time is small. And this, this will have like an impact, as we will see later. Okay, any questions?
Yes, how we can correlate this with the delay spread? So the delay spread is the spherical of the coherent bandwidth.
Yeah, delay spread is basically you start to get, so you transmit a signal, you get copies of that signal, arriving from different paths, and then there is the earliest copy, and then there is sort of the last copy, and the time difference is the delay spread. That's the delay spread.
Yes.
Yeah. And the delay spread, it is the inverse of the coherence bandwidth of the channel. So the coherence bandwidth of the channel is a statement about the channel gain in the frequency domain. So basically you say, okay, in the frequency domain, okay, how is the channel gain at F1 and F2 related? And you ask this question regardless of mobility. So actually when we studied the correlation in the frequency domain, we actually said V equal to 0. So I'm saying, assuming that actually there is no mobility whatsoever and basically nothing is changing over time, how is the channel gain at F1 and F2 related? But now I introduced the time dependent factor, okay, and now we have a change over time. Now I am talking about the channel gain now, okay, the channel gain now and after after some time, so at T1 and T2, or at T1 and at T1 plus delta T. So that's a correlation across time. Okay, can you study both at the same time? Can you have like a study, because you may think that definitely, what about the function that examines basically the channel gain at F1 and T1 versus at F2 and T2? So you play large. You basically go for, so it's like you do the previous analysis with time variations. This analysis is there. It's in the literature. Okay, I will just not deal with. So basically, I'm trying to to extract from channel modeling the stuff that we will need for this course. Because as I said in the previous, channel modeling is very good. But again, if you want like to be as accurate as possible, you should study correlation across frequency and time at the same time. But it will be less. So for us, it's enough basically to proceed like this, like to have this times, sort of this separation. Yes, so, if you wonder, there is a function phi delta F delta T. Okay, so it's two-dimensional function. It's not very easy to visualize and understand, but it is there. And again, channel modeling is not easy. Okay, you can take a full course on it. Okay. Now, so we talked about delay spread, coherence, bandwidth of the channel, coherence time, right? So sometimes you find people in papers talking about Doppler spread. Doppler spread. And so what is Doppler spread? Basically, it's another way of talking about the coherence time. It's another way to talk about the coherence time. So let's try again to have a glimpse about its what is this business of Doppler spread. Okay, so I'll try again to make things as simple as possible. Suppose that, I mean, we don't do this in an actual communication system, but suppose that we just transmit a pure tone. So suppose that you just send from the transmitter a sinusoidal signal with frequency f0. That's it. Okay, so that no symbols, nothing, so that we can focus on what happens to this pure tone. Okay, so again, if you have symbols, things will be complicated. So just suppose that your baseband signal is e to the I 2 pi f0 t, and now this becomes your s of t. So s of t is just this signal here, and it is multiplied by g of t, and now this is the received signal. We are interested in the power spectral density of the received signal. So basically, how does this signal look in the frequency domain? But because g of t inside it, okay, let me actually write it, right? So g of t is this thing, and it has random variables t tau. It has random variables alpha, and this guy here, it has this theta, right? So now things become random, and basically for random signals, we define the Fourier transform using this concept of a power spectral density, which again you may have studied in 241. Okay, so for us here, I mean, I need just to take it for granted that the power spectral density of a wide sense stationary random process is simply the Fourier transform of its correlation function. Okay, so if I'm interested in the power spectral density of y of t, then I need to go and obtain its correlation function, time correlation function, and then take the Fourier transform of this, and this will be the power spectral density. Okay, for a general x of alpha random, so this is wide sense stationary x of alpha. The original definition of power spectral density is that you take x of alpha, you take its Fourier transform, but you do a truncated transform. You do not take it from integral from minus infinity to infinity. You take a truncated transform like this from minus t to t, and then you scale by 1 over then you take the magnitude squared. Take the magnitude squared, okay, and then you take expectation because your stuff is random, and then you scale by 1 over 2t, and then you take the limit as t goes to infinity. That's the main definition of power spectral density for a wide sense stationary process. Again, it's sort of, you take a truncated Fourier transform, you take its magnitude squared, okay, and so that's the reason that power spectral density is always something that is non-negative and real valued and non-negative. It's because by definition it is a magnitude square, and then you take expectation because you have random stuff, and then you basically normalize it and take the limit as big T goes to infinity. You can show that under some conditions, it's not always true, that you can start from this expression here and show that the power spectral density is indeed the Fourier transform of the correlation function of the process. So this is the correlation function. So the correlation function, you apply the definition, and basically the correlation function of signal y will depend on the correlation function of g. And the correlation function of g basically we obtained on the previous page. So this is the correlation function. Okay, so this is the correlation function in time. Correlation function. See, things here are sort of messy, right? So we have correlation function in frequency and correlation function in time, again because we are going back and forth between time and frequency. Okay, and so you just need to focus here. Okay, so this is correlation function, and this is what was derived in the previous slide. I mean, but power spectral density, you need to take the Fourier transform. So I need to take the Fourier transform of this thing, and so we need to take the Fourier transform of the Bessel function. And the way that we will do it is that we will basically express the Bessel function again as an integral. Okay, so we will to be able to basically do the derivation and get a closed form for the power spectral density. What we will do is that we will take the Bessel function and rewrite it as this annoying integral. Okay, which is this guy with the factor 1 over 2 pi. This factor here is what I called A. So this integral here is the Bessel function. This outside integral is the CTFT integral, right? So you want this function, if you want its CTFT, so you just multiply by e to the minus I 2 pi f delta t d delta t. Okay, so our variable here, our argument is delta t, the time separation, and this will be one integral, and then there is this second integral which comes from, again, representing it comes from the integral representation of the Bessel function. Okay, then what we do here, we will, since we already made lots of assumptions, let's just assume that we can also interchange the order of operations. And so we can interchange the order of these two integrals. So basically these two integrals, if you want the strict order, you need to integrate first with respect to theta, then with respect to delta t. So let's suppose that we can integrate first with respect to delta t. When you integrate with respect to delta t, you just have the integrals of those exponentials. You can combine them together, and then you can use this integration here that you know from signals and systems. That basically, if you have an integral from minus infinity to infinity, e to the plus or minus I 2 pi, and then you have a variable z and another variable, another real valued variable w. If you integrate with respect to z, then this thing here is the Dirac delta of w. Okay, so we'll use this here. So we are integrating with respect to delta t, and delta t is multiplied by stuff. Okay, and so basically the result of this integral with respect to delta t will be the Dirac delta of this thing here. Okay, so applying this rule, we have this basically integration. So now we are stuck in something else. So now the Dirac delta is not like it's not like the Dirac delta at the beginning of the lecture. The other one was like delta of tau prime minus tau, and so basically the integration is just that you replace each tau prime by tau. But now our problem is that we are integrating with respect to theta, and inside the delta we have a function of theta. It's not just theta minus something. It's not just time shift or something, or like it's not just a shift. It's cosine theta, and so we need actually to again use this result for the Dirac delta. That the Dirac delta composed with function g. I don't think it was smart to use g, because g. Okay, so this is very stupid actually. Okay, so sorry. I should have used another name. Okay, because we are already using g to mean the channel gain. Another name. Okay, so call it ipsi or something. Ipsi. So delta of ipsi of theta. So this is delta applied to a function. We have basically some rule telling you that suppose that this function is differentiable. Okay, so we'll assume that, and cosine theta is differentiable. Good. And suppose that the first derivative is a continuous function. This is also applicable to cosine, because actually cosine is infinitely differentiable and all its derivatives are continuous. Good. And suppose that you obtain where this function inside the Dirac delta is equal to 0. So we search for where the function is equal to 0, and at the same time, basically if the function is equal to 0 at theta j, it should not be equal. The first derivative of the function should not be equal to 0 at the same theta. Okay, so the rules are psi is differentiable. Its first derivative is continuous. There is theta j such that psi of theta j is equal to 0, and the first derivative evaluated at theta j is not equal to 0. If all these conditions are satisfied, then delta of psi of theta can be written as a sum, because maybe the function is equal to 0 at several theta j's. So it is a summation with Dirac delta of theta minus theta j, and then you need to divide by the first derivative of the function psi evaluated at theta j. And you can appreciate now why this condition is needed, because we will actually divide by the value of the first derivative, so we don't want to divide by 0. Okay, so let's apply this here again. So my function is theta, psi theta. Okay, so it is this function which is inside the Dirac delta here. Its first derivative is minus v over lambda sine theta. Okay, let's try. So when is this function equal to 0? And of course we are interested in the interval from 0 to 2 pi. So we know that the cosine it's there from minus infinity to infinity, but because we are integrating from 0 to 2 pi, this will be our domain of interest. So we ask ourselves, where is this function equal to? Suppose that it is equal to 0 at theta tilde. Okay, then equate this thing to 0, and you'll find that this leads that cosine theta tilde must be equal to this quantity. Now this is a bit tricky. So because we are not sure that the right hand side is actually between -1 and 1. F is the frequency variable, and the frequency variable when you do Fourier transform is from minus infinity to infinity. F0 is just the given number. It's the, remember we are basically transmitting a pure tone at F0, and there is V and lambda, those are constants. So again, because we are doing Fourier transform, we are basically doing this thing for any F that is real valued, and no guarantees that basically this part is between +1 or -1. Okay, so we have two possibilities. If this guy in absolute value is greater than 1, then there is no real valued theta tilde that will actually satisfy this equation. Okay, and so psi theta will not be equal to 0 at any real valued theta, and this means that the Dirac delta is 0, and we have a 0. But if this quantity here is less than or equal to 1, then you can find the solution. In fact, there are two solutions, right? Because what is the cosine signal from 0 to 2 pi? From 0 to 2 pi, okay, it looks like this. Okay, it looks like this. So here is pi over 2, then here is pi, then it goes like this, right? To 2 pi, and this is at pi, right? So this is the cosine. This is the cosine signal. Basically from 0 to 2 pi, and if you equate cosine to something, except at those 3 points which you can ignore, there are two solutions, right? So two solutions, this point and this point. If you take here two solutions, and at the point, the points at which basically you have this, the problems here and there, they can be ignored. Basically those are 3 points, a set of measure 0, and so in terms of the integral, basically the integral is blind to these points. So basically we need this condition to get a non-zero result, so that we can solve the equation that cosine theta is equal to something. You need this thing to be living between -1 and 1, and there are two solutions. You get them by the cosine inverse. Okay, and suppose that you get this cosine inverse okay, to be the smaller value, and then you have 2 pi minus this cosine inverse of f minus f0 over v over lambda. Okay, and to apply our formula, we need basically the first derivative of the psi function evaluated at basically where the function is equal to 0. Okay, and so I will take this function, and the derivative is sign. The nice thing is that actually we need the absolute value of the function. So if there is a minus sign, it can just be it's absolute value of -1 is 1. And so whether we are talking about this term or that term, what we have is v over lambda, the absolute value of sine of cosine inverse, right? This guy will give you a minus sign that basically, because we take the absolute value, they are both will give the same result. And what is sine of cosine inverse? You can just have this triangle here, And so the triangle here tells you, so you can imagine that the angle that we are talking about is basically this angle. So its cosine is f minus f0 over v over lambda. So you can, so basically this is the adjacent, f minus f0. This is the hypotenuse, v over lambda. And so the opposite can be obtained by Pythagoras. And sine of cosine inverse will basically be the opposite over the hypotenuse. So it will be basically this quantity here. Okay, so the sine is square root v over lambda squared minus f0 squared, and then you divide by the hypotenuse, which is v over lambda. But there is a v over lambda here, and so this is basically what you need to have in the denominator. Okay. So, and this is true for this theta tilde, and for this other value of theta tilde again, because, you know, we are not just computing the value of the first derivative, we are taking the absolute value. Okay, and so now we are done. The power spectral density of y will be 2 Dirac deltas. Why 2 Dirac deltas? Why again? Because we started with a function of a Dirac delta, and this function is equal to 0 at 2 values of theta. Okay, so so the rule is that you should have a number of terms equal to the number of points at which the function inside the Dirac delta is equal to 0. Okay, so we will have basically 2 solutions, so 2 Dirac deltas, one at this angle and one at the other angle. But this is actually true only when this condition is satisfied, because again, like, you end up with the cosine equal to something, and this thing should be in magnitude being should be less than or equal to 1, so that you can solve. And the denominator is the same for these 2 Dirac deltas, and so you can take it as a common factor. Okay. Now the integral now with respect to the Dirac delta is straightforward, because this is a Dirac delta of theta minus something. Okay, and basically, if this angle lives between 0 and 2 pi, okay, which is our case here, then the integral of the Dirac delta is 1. Okay, so you get a 1 from this Dirac delta, you get a 1 from that Dirac delta, and so you get a 2. And okay, so it seems that this should be a 2 here. Okay, so I will put it 2 and then I will check, because, like, yeah, you have 2 Dirac deltas, and both are actually inside from 0 to 2 pi, and so basically it should give you, I think it should give you a 2. Okay, but let me review it later. Okay. So this is the power spectral density. So the nice thing here is that we have actually closed form for the power spectral density. Closed form. Okay, and what is this thing? So here it is. So this is sort of, so you can say this thing is the spectrum of the received signal when we transmit a pure tone at f0. So you transmit a signal that in the frequency domain is just a Dirac delta at f0, just a spectral component at f0. That's it. It's a pure tone. But when there is mobility, what you get is not a signal just at f0. It's a signal with a power spectral density that is non-zero, extending from f0 minus f over lambda to f0 plus f over lambda. This will never happen in an LTI system. In an LTI system, if you feed the system with a pure tone, with a sinusoidal signal, as an output, you get a sinusoidal signal with the exact same frequency, perhaps with a modified amplitude and phase, but the exact same frequency. Our system here is not LTI. If V is not equal to 0, then actually our system is linear and time varying. time varying systems can cause something like this. You input to a system a sinusoidal signal with a frequency f0, but at the output of the system, you get spectral components, not just at f0, but in a range. And this range in our specific problem is from f0 minus v over lambda to f0 plus v over lambda. So this effect is called Doppler broadening. Right? You transmit something with a width of 0, right? A frequency f0 exactly, but then you get basically a spectrum extending over an interval of frequencies. So this is called Doppler broadening, and this happens due to the Doppler frequency, due to mobility. Okay, no mobility, you will not see this thing. But because of mobility, you will basically get this received spectrum. Okay. Now this is a width, right? So basically, the spectrum here is not extending from minus infinity to infinity. In fact, it lives between these two guys, and so it's like this power spectral density. It has a width, and this width is called the Doppler spread. The Doppler spread of the channel. And the Doppler spread of the channel, what is the width? It's proportional to V over lambda. It is proportional to V over lambda. You go to the previous page, you will find that basically the width of the time correlation function is something that is proportional to lambda over V. So basically, the Doppler spread is almost the reciprocal of the coherence time of the channel. So some people, for some reason, rather than talking in terms of the coherence time of the channel, they will tell you, oh, this channel, it has a high Doppler spread. High Doppler spread means a small coherence time. Is this result surprising? No. I mean, so basically, so the Doppler spread being the reciprocal of the coherence time, no, it's not that surprising if you know Fourier analysis, because Doppler spread is the width of the power spectral density, and the power spectral density is the Fourier transform of basically this of the correlation function. Okay, and so it is expected by the uncertainty principle that the width of this function will be the reciprocal of the width of the power spectral density. And so this is another relationship